Welcome to the motor control project of the School of Engineering at UAC. Today we present reduced voltage start implement with serial resistors. The project focuses on controlling the startup of a three-phase motor, whose characteristics are a power of 0.5 horsepower and 220 volts supply voltage and 1.6 amperes nominal current. The inrush current peak in 5.05 times the nominal current. Our main objective is to limit this current peak to reduce mechanical stress and voltage drops on the line. Analyze target current. Well, first, we calculate the initial inrush current by multiplying the factor by the nominal current, that is 5.05 times 1.6 equals 8.08 amperes. The goal is to limit the current to 85% of its natural starting peak. This gives a limited current of 8.08 times 0.85, that equals 6.87 amperes. Analyze required voltage. To reach the target of 6.87 amperes, we must apply a reduced voltage to the motor. The phase voltage is 220 divided by the square root of 3, that equals 127.02 volts. The reduced voltage required at the motor terminals is calculated to be 21.38 volts to achieve the desired current limitation. Resistor calculation. Using the vector triangular method, the voltage drop across the resistor is estimated to be 107.8 volts. Applying Ohm's law, the required resistance value is 13.4 ohms. The power dissipation is Ia squared 2 times R, resulting in 1.88 kilowatts, which demands a robust resistor bank capable of handling this dissipation during startup. Selection. Protection. We select a Eaton TGB WU1B020 power breaker. Although the nominal motor current is 1.6 amperes, the breaker must withstand the inrush of 8 amperes. A range of 10 to 16 amperes provides a safe margin. For overload protection, we use a Schneider LRD12 terminal relay, essential for overheating protection, since its race includes the nominal current of 1.6 amperes. Selection. Control logic. The main contactor selected is a Schneider LC1D09 AC2 rated for motor loads. Its 9 amperes capacity safely supports the 8.08 amperes inrush. For the control sequence, we choose a Krausen 8827120 timer, adjustable for 0.1 to 30 seconds, allowing us to tune the optimal delay before bypassing the resistors. Resistor bank. The requirement is 13.4 ohms with a dissipation capacity of 1.88 kilowatts. The implementation was done using a custom-built bank of Wire 1 power resistor, individual 15 ohms divided by 50 watts resistor were arranged in parallel or series combination to meet the 13.4 ohms requirement. Simulation. Before the physical assembly, we validated logic in CAD-SIMU. We verified the startup sequence, resistor on, timer delay, resistor off, and confirmed the proper safety interlocks. Power diagram. In the power diagram, energy enters through L1, L2, L3. Device Q is the main protective circuit breaker. Contactor KM2 connects the resistor R in series with the motor of reduced voltage starting. Afterward, contactor KM1 activities to bypass the resistor and feed the motor at full voltage. Thermal relay F protects the motor against overloads. Stage 1. Startup. When the start button S is pressed, the KM2 coil and the timer T are energized simultaneously. The resistor bank R connects in series with motor M1. The auxiliary contactor of KM2 closed to latch the circuit, and motor 1 begins accelerating under reduced voltage. Stage 2. Normal operation. When the timer T completes countdown, its auxiliary contact closes, energizing the KM1 coil. KM1 closes, connecting the motor directly to the supply. Simultaneously, the timer auxiliary contact of the opens. The energizing came to opens, removing the resistor bank R from the circuit, leaving the motor operation at full voltage. Implementation and calibration. The control on power circuits was assembled on the test panel. Calibration was crucial. Using a digital multimeter, we adjust the resistor bank connection until we measure exactly 13.4 ohms, matching the theoretical requirement. Experimental results. Using a clamp ammeter and oscilloscope, we measure the actual starting current. The estimated direct online start current was 16.8 amperes. Our theoretical target was 6.8 amperes. The measured reduced voltage start value was 7.2 amperes. We achieved approximately 57% reduction in starting current compared to direct start. Current waveform analysis. On the oscilloscope, we observed two stages. When starting with KM2 closed, a high current peak appeared, but lower than the direct start peak thanks to the resistor bank. During the full voltage transition with KM1 closed and KM2 opens, a second peak appeared, significantly smaller because the motor had already reached substantial speed. After this smaller peak, the current quickly stabilized at its nominal value. This project demonstrated that resistor startup is a reliable and cost-effective method to reduce electrical stress on motors. The key to success was the precise calculation of the 13.4 ohms resistance and the proper selection of AC3 contactors, allowing a safe current limitation of 57%.